Hi everyone, I'm Ilo also, but most of the slides are prepared by Colleen. Okay, so we just close the door.
Yeah, it's okay. We'll figure it out. I mean, the audio is recorded, so that's fine.
Colleen, probably she's muted right now. And she's muted right now. Later, she will talk a few things. So, okay. So I'm curious, like how many of you have ever used OpenMP threading and trying offload? No, okay.
I'm a beginner.
Huh?
I'm a beginner.
Oh yeah, beginner. That's good. I can brainwash you. So okay. So I will go through a bit the OpenMP offload status on Polaris. So the target machine we will have exercise on about how to set up the environment, possible compilers you can use for building, running. There's some demo cases you can do, just do your hands-on, log on, get an interactive job, get a node and run things on Polaris. If we're talking about multi-GPU runs, because Polaris has 4 GPUs on each node, so if you just leave, you don't do it properly, you just leave them wasted. It's like you have your CPU run, then if you don't put the CPU core affinity right, you will just waste the resource. So it's a critical thing you have to do. But now with both CPU and GPU, it gets further complicated. So there are also hands-on examples. Colleen will talk about what she did on games, try to get performance. Because we were so comfortable programming CPU for decades. As long as the code is fine running, you don't really care if they're on your critical path. But with GPU porting, you do need to put an effort to think about your code, doing necessary changes to extract the performance, because it's very likely for a 5% portion, if you don't take it seriously, it becomes 10 times even slower. And as the rest, 90%, you could accelerate them into a 10%. So you see the way it's changed, the dynamics change a lot. So the last portion I will talk about, maybe play with you a bit debugging, because actually GPU programming, now you are not programming with a vendor provided programming model. You kind of have an abstraction layer that is OpenMP on top of it. So that adds a bit difficulty, but actually it's not that difficult. You need to know how to do it. So the last portion, you will be free to play with whatever you are interested in, and I will be around, and Colleen's around to help you out. So so let's quickly go through those technical things. So on Polaris, we have several compilers available for you, but okay, how does it? There's the first one, NVHPC. Don't get confused. So NVIDIA shipped 2 sets of things. One is called the HPC SDK, which ships you the Fortran C++ compiler. There's another thing called CUDA Toolkit, which ships MVCC, which is the CUDA compiler for the CUDA language. So don't get confused. All listed here, because OpenMP is you are programming a host code with directives. So you need is a host compiler. It's a regular CPU compiler with OpenMP offload support. So what you care about is the host compiler. So here, host compiler from NVIDIA is called NVHPC in brief. It has the on Polaris. It does support regular CPU threading plus the GPU the GPU support. You can turn on the OpenMP offload. Technically, think about it. NVIDIA compiler support OpenCC. There's a lot of similarities between OpenMP and OpenCC. So they just added about a few years ago, since Perlmutter was being online, and NERSC DOE just paid through NERSC to ask NVIDIA to enable OpenMP offload support. So the OpenMP offload is there. I don't know how much you need OpenMP CPU support. I know that there's only one limitation on NVHPC compilers. OpenMP tasking is not supported. So as long as you're just okay with doing OpenMP threading, it's fine. The second one is, you see, have a very distinct name, the module name, because this module is not through the Cray programming environment. It is supported by the users at ALCF or the ALCF staff. The reason was the Cray doesn't directly support upstream, the open source LVM compiler. It doesn't install it for you. But for our users, we are very happy with the LVM compiler, but we also need the MPI. So we provide this MPI wrappers, giving you standard MPI CC, MPI 90, those things for you to just run your MPI program with offload. So it does support CPU and GPU. I would say language-wise, the OpenMP standard spec support-wise, LVM is the most advanced one. Just one catch, there's no Fortran. There is Fortran. So the latest one, LVM 17 I installed, has Flan. It's called Flan-new. So there's a long history of the chaos in naming who claims the name of Flan. But anyway, the latest LVM has a Fortran compiler, although it doesn't support OpenMP offload yet. So that's the current situation. The GNU one, so you have the CPU support, there's no GPU support. I personally, my personal experience is, if you not on the Polaris machine, GNU one is actually good as a development tool because it supports quite reasonable feature subset of OpenMP. The only downside is the performance is not great. So you can't really use it for production. If you just want to develop codes, if you have a GPU enabled GNU, that's also doable. The last one is Cray. So I guess the Cray one is LVM based, but Cray one has so the Cray has the C++ portion and Fortran portion. The Fortran portion, FTN front end, is Cray own proprietary kind of technology, but the C++ one is largely CLAMP plus libraries provided by Cray, so it's a kind of a hybridization. I would say if you're doing CPU, you don't need Cray because you can. If you just need a C++, you don't need Cray. You can use LVM or NVHPC for offload. If you have Fortran, you can also do NVHPC. So it's not really necessary to touch the Cray one. However, if you work cross-platform, for example, you work on Frontier machine, that because on that machine, Cray Fortran is the only one support OpenMP offload with reasonable support. So you can also play with it on the Polaris machine, although as we noted, it's not a recommended one. Okay, so for NVHPC, so since it's programming environment, you have lower CC, capital CC, and FTN as the MPI wrapper. And if you need to do certain debugging work, you don't want to deal with the MPI, you can just use the native C++ Fortran compiler directly and turn off your MPI in your code. So this CPU, I have typo. CPU flag actually it should just -MP. There's a equal if you don't put GPU, I think there's fine-grained control, but usually you just need dash MP. The GPU flag is you need to set dash MP equal GPU means you're turning on OpenMP offload dash GPU. Keep in mind, even you set dash equal GPU, it doesn't mean your OpenMP like parallel flow will be automatically offloaded. It just means that you have GPU path enabled. Your regular OpenMP threading will still work. So you can have a code mixing certain portion with OpenMP threading, some portion with OpenMP target offload. So you can set dash GPU equals CC80. I think you can also choose like CUDA toolkit, CUDA versions, because if you have ever installed the HPC compiler, you have two ways of installing it. One is ship with one version of CUDA toolkit. The other way is you have 3 versions of CUDA toolkit. So if your installation have 3, you might need to select a specific CUDA toolkit version to use with your NVHPC compiler. So it's a bit messy, but if you're lazy, you can just don't put dash GPU, you just dash GPU equals CC80. That means your compiler will compile your offload kernel for every version of CUDA NVIDIA GPU that NVIDIA sells. Yeah, if you don't have a crazy code, you can just leave that. But my experience, especially you are doing CI, you have 1 core, probably you want to set this flag just to reduce the compilation time. My experience on Pona Espresso, with this flag, 1 core, 1 hour and a half. Without this 3 hours, you are still compiling. So it's optional, but it's still recommended. Yeah.
So sorry, I missed what you said. So when it's version dependent, how is it different? So you have minus MP equal to GPU, right? But that doesn't specify the version.
Right now, it's HPC have a default version of CUDA toolkit selected as you install it.
I mean by module load.
No, you cannot control it. Because NVHPC, the compiler, will invoke all the tool chains from CUDA toolkit. The CUDA toolkit is shipped inside NVHPC. Maybe I can, next slide, I will give you a bit more insight about how to control that. But for NVHPC specifically, if you want to use a version of CUDA toolkit that's different from the default one, that version you specify after this dash GPU equal, I don't remember exactly, but there's like a 10.1 or 11.0, you can control it. But you cannot use any, like a random CUDA toolkit installation on the disk. You find a version of 12, you can't use it. You can only use the one.
You're talking about Polaris?
On Polaris, yeah. Because it's great chaos anyway. And let's unfortunately. So just remember, if you want to select the GPU, minimize your compilation time, just put the dash GPU equals CC80. We only have one kind of GPU, A100. Yeah. So the second is the LVM1. So LVM1, the only difference is it's not capital CCFT, it's just regular MPIC, MPICC, MPICXX. So it's actually a lot of, it's more friendly to users. As I said, Fortran is 11, LVM17. In that release, you have a CPU only one. So CPU flag F-F OpenMP, GPU flag. With the latest one, you can select offload arc equal SM80, which is CC80, so it's A100, or you put native. Then it would auto detect what GPU is available and put it for you. So, but you do need to set offload arc. Some older version of Clan, you can use that one because I just found that one is too hard to memorize. So I stopped using that. I tend to use the easy one. Yeah, so that's basically how to invoke the LVM for offload. So if you have, not on Polaris, but if you have a machine that have like A100, H100, like you want to compile it once, you can just put a list separate by comma. So it will support all the one versions you listed. It's easier for testing, development work.
So what happened in the hypothetical situation when you have two different classes of GPU? You have A100, you have an earlier version of GPU or something like that. So native will just detect anyone.
No, I think native will get the first one it finds. Yeah, but if you do, because native, it's like you build on CPU cross-platform, you say native, it's only the one that you're currently on. So it's hard to elaborate all of them. But you can put SM_80, SM_70, and 89, put a long list, and the kernel, offload kernel, will compile for every GPU architecture listed and linked into the executable eventually. Then this executable is runnable on any of those machines. Yeah. So, oh yeah, just go back, because on Cray machine, the CUDA toolkit is faked out of the NVHPC installation. We have users could not find that one not easily workable, and Cray tightly control the deployment of NVHPC versions. So that's why we were doing CPU separate modules, CUDA toolkit standalone. So like if you have a CPU code plus CUDA language, just your daily job work scenarios using GNU plus CUDA toolkit. So you can use the toolkit standalone model to select the version you want. That is the public release. It's the same, exactly the same as your workstation desktop. So unlike the NVHPC scenario, it's some kind of extracted a long list of passes just to make it work. Pretend it to be CUDA toolkit. So we used to find that one difficult. So if just repeat this: if you use NVHPC, stick to what Cray offers. If you use GNU VM, just use the standalone modules. This is very similar to our daily machine. So with the CUDA toolkit standalone, because ALCF staff install that for on the machine, so we keep it more frequently updated. So you have more freedom to select specific version or the latest version. Yeah. Okay. So the GNU one. So for the GNU one, it doesn't support offload. So you better unload that Cray acceleration architecture module that was Cray handled, because that module will stack something in your linker line, but your compiler doesn't handle the GPU part, so it will cry. So you just unload it. Then the CCFD and all those are the same. Then offload flag is actually OpenMP. So the last one is the Cray compiler. If you do use them, if again, yeah, for CPU only you unload that module, but for your GPU,
so the newer version of GCC that supports offloading is not installed yet.
it's not installed. Yeah. Technically, you can request we can install it in alternative locations, but likely it will be on your own. We won't provide a programming environment GNU to support that when we deploy, because Cray doesn't want to take responsibility for sure. So sure, but on the other hand, if you're a Ninja programmer, right, you can do like what we did for LVM. You just dig out the MPICH and marry it with the GNU we installed, so it will eventually work. So this is the script running on Polaris, because this is more like script mode. You provide JavaScript to run it. Just keep in mind put this PBS current work directly. Otherwise, it default to your home and it could not find your executable. So just add that one particularly. All the attributes I think are required as for today. You probably are not familiar with the file system attribute. That's ALCF because we have multiple file systems. When a file system is down, the jobs specify requirement on that file system won't be sent to run. So it's a safety mechanism. Otherwise, if file system down, but your job still gets scheduled, you request data from that file system, your job just dies. So it's a waste of your time. So that's why you need to specify that one.
Versus if it doesn't fail, it just hangs.
It doesn't, well, fails are flagged by the staff, the people who maintain the storage. If they find that it's necessary to stop all the jobs dependent on that one, they will just flag it in the PBS system and you won't hit the headings.
So I'm trying to clarify what you just said. So now we specify the file system is equal, right?
Home and eagle.
Home and equal.
Home, usually we have executables left on our home, or you have some lightweight data you want to read from your home. That's why it says home. Eagle is usually your project for directory, the scratch space. Yeah.
So you're saying you want to specify more than one file system when you run the job, right?
Yeah. Is this for example, your job needs executable from your home and needs to do the input file and write the output file from your project directory that is on Eagle. You specify both. If the admin find that Eagle is not reliable now, it will flag the Eagle, and your job, if it hasn't started, will just pause. Like it will not pause, it will be still queued, but won't enter the state of running.
Will it still move up in the queue while it's being queued?
Yeah, it's not suspended. It will
will.
still accumulate
So
your
it's still
scores.
sitting at the top of the queue, and
But
as soon
not
as
running.
as soon as the file system comes up.
Yes. Yeah, it will keep with the usual way of escalating in the queue.
So like some projects may use Eagle and some may use Grand, let's say, right? So the idea is if one of the two file systems is dead, then it can still run jobs that use the other one and do something useful while they're working.
Yeah, and Polaris has access to both, right? And I'm usually running on Grand, so I could just do that on Polaris as well, right?
I think so.
So when you apply for allocation, don't you have to specify which file system you want? Or you can have access to any file system?
Actually, because I never went to the application phase, I don't know the exact answer. Post a question on the Slack, I think people will.
I didn't remember that there's a default allocation on each of them.
But I think that I'm not really sure what the
I probably
policy
only have
is either. I think that most things are allocated on Eagle, and if you have some export requirements, you may get one on Grand or something like that.
We are on Grand, but we used to be on the one that's disappearing very soon. What's that called?
The Theta?
It's like machine.
No, Theta's not the file system.
It's the file system.
Yeah,
for
it's
Theta.
like.
Yeah, but it was not, it had an
FS.
FS0 or?
Yeah, that's the
Theta
Theta
is your-
Yeah.
cluster file system. Yeah. Okay.
So then why don't we just specify all the file systems that we're eligible every time?
No, but then you're not eligible as soon as one of them is down, even though you never write anything to it. Because if I put in Grand as the only one, then I don't care if Eagle is down.
So what I'm saying is, why don't you just put home, Eagle, and Grant every time you run something?
That means that
Your job
Yeah.
will be
Be there forever?
will be sit there, and if any of them are down, it won't run.
It's a safe option, but you sit longer in the queue than necessary. Unless the machine is always up, but.
Yeah. So
We're still at.
during the hands-on, I think likely we will use the interactive mode to just submit with dash I. Sorry. Oh, okay. Well, this is with a JavaScript, but if you just replace the JavaScript with dash I capital, it will be interactive. That's the only difference between interactive or script. Okay. So this is the demo.
Can we have this file, like can you upload it or?
It's a Git repository. You clone the Git, you will get the.
So I mean, the slides, can you upload the slides so that we can just copy and paste?
Fine, give me 1 second. Let me put it into the Slack slides, I think.
Yes, which was, okay, I was thinking that was my problem. So,
You said the one thing on.
And I uploaded the slide exports to the Slack slides channel.
Oh, you mean, oh, Lord. See,
Appreciate it. Yeah, now it will work. And also.
I also have, in the build, SSH, there's this stuff. which obviously
No,
is-
no, you don't need to change.
Kill all that.
Yeah. So you don't use this now, just type cmake. Okay, create a directory. No, not here. Okay,
So I still have this ugly directory. I can put it.
no, go to the build. Cmake.
If you have anything to add, just unmute.
That's.
Can you guys hear me?
Yes, we can hear you.
Okay, yeah, no, nothing, Ted, I was just gonna ask, do you want me to do the demo or do you want to do it?
I don't know, what's your best experience on doing this demo?
I mean, I can do it because I've done it many times, it's always just like my voice might go out, so then you can jump in.
Go ahead and do it, yeah.
Oh.
Can you share screen?
Yes. I should be able to. Yes,
Stop sharing. Stop sharing.
So this is the one that's. Saves messages kind of on there.
go share
Recording still going here.
just two. Okay. Can you see that okay? So share. Can you guys see that okay?
Let's make it larger. The fonts are very small right now.
So actually, I'm gonna open a couple more windows just to make it easier.
We can see your terminal, but it's
Yeah,
very
sorry. I'm still, yeah, give me a second. I'm gonna open just a couple of other windows so that it's easier to see. And this is just. I'm just going with the I already cloned the repo. I'm just going to the location. So the CD as of hands-on for levels of OpenMP demo.
I pushed some changes this morning, very light ones, mostly like compiler options. You get
Okay. Oh, to the repo itself?
Yeah.
Okay, I didn't have a chance, sorry.
And just pull this pull should be straightforward.
Actually, this is where I want to go. Oh, great. Okay, I think. Oh. I have a separate branch. Okay, yeah, next. What? I'm still just setting up. I like to have like 4 windows open for this. Because of it.
Just want to run the repetition function. Yeah.
Colleen, the fonts are still pretty small.
Got it, yeah. Hopefully that's okay. Is that good?
More.
Or big?
Significantly more.
Okay. Oh, better?
Better.
Well, probably please figure. Hopefully this is readable. Okay. Okay, so I think it's ready to go. So this is just going through, like EA said, I also have on program levels OpenMP. And this is so I already get cloned it and I get pulled. So I got updates from EA. So if you go here into the demo folder, you'll see a README and then a Fortran and a C++ section. So the README is basically what I'll be going through, and yay, please jump in if I say anything wrong, of course. And then I'll go through, I'm gonna be compiling and running the C++ ones, but I'll show the Fortran ones as well in a separate window. And feel free, if you are a Fortran person, I'm also primarily a Fortran person, so please feel free if you want to follow along. You can do the same thing as what I'm doing, but in Fortran, because I'm literally going to be mostly copy pasting from the README, so hopefully it's pretty easy to follow along. So everything's okay to see? Yeah, let me know if something is hard to see. So okay, so to get started, so this is just gonna go through like the very basics. So it's the 101 demo. Please interrupt if you have questions. I think Ye mentioned when he was giving his talk, he talks to the OpenMP committee and has a lot of experience with even the coding below the OpenMP standard itself. So he's a very good expert. And of course, I've done a lot of programming from Polaris looking up as well. And the whole point of this is to help you guys. So if at any point something you don't understand, just feel free to jump in and ask a question. And this is very basic level OpenMP offload. So if you're already beyond this, it's fine. You can feel free to turn your brain off or work on something else. So let's get started. Yeah, so basic stuff is like I said in the talk, offloading code to the device and using OpenMP to look at device info, expressing parallelism, and so that you can use all the GPU, and then mapping data so you can move data from the CPU to the GPU. Those are the main topics that were covered here. So I already grabbed an interactive node. It's also in the README if you want. Hopefully you can all get interactive nodes. And then, like he talked about, the first thing is setting the environment. So you can do this, at least for the C++ side, either with the LLVM environment here. So you would do module load MPI wrappers, mpitch, or module, and then module load CUDA toolkit, and then copy the LLVM makefile to makefile, and then we just use the makefile. Or you can use the default program environment NVHBC. I would recommend swapping the default NVHBC module is 21.9. I would recommend using the newer 23.3 and then copying makefile NVIDIA to makefile. I'm gonna go ahead and do NVHBC, but it is kind of interesting to also do it with LLVM and then see where they differ at all. I'll point out ones which I know LLVM and NVIDIA do slightly different things. So module list, I should already have NVHBC loaded, but I still have the older NVHBC 21.9. So I'm just gonna do module stuff. NVHBC 21.9, NVHBC 23.3.
Sorry, Colleen, which file are you looking at?
This is the README. If you clone the repo and then CD into programming modules OpenMP demo, there should be a file called readme.md. And if you open that, you should see this file. Did that work?
Let me see. I am looking at README MD, but it doesn't really have anything on it. Yeah, come back.
Are you up one directory by any chance?
OpenMP.
Are other people having the same problem, or should I can check on GitHub quickly.
Yeah.
Okay, I found it.
Oh, cool. Okay, and then just so everything's good. Oh, CD into CP. And then and then you have to choose which one or CVP. So I'm just gonna go with C++ at the moment and NVIDIA makefile. Okay, and if we look at the makefile, okay, so that should say NVIDIA, but we see the flags that Ye mentioned: CC, MP GPU, MP -GPU equals CC8. Okay, so let's start with the first example. So that is this one. This is the most basic thing you can possibly do. So first thing, querying the environment with OpenMP. So OpenMP has certain convenience functions which will tell you about the system you're running on. So here you can ask OpenMP, how many devices do I have? So that would be GPUs in this case. So right side is C++, left side is Fortran. So it won't pick devices, so it'll just print number of devices open in PCs. So the same thing in C++ to Fortran. So the next, the most basic thing you can do is just have a target region, target, or exclamation point hash or a $OMP target. And this is the thing that says start executing on the GPU. So over here, CPU, there's a thread on CPU running along until it hits the OMP target, at which point pauses, and then a thread on the GPU starts, and the GPU will run the stuff inside the curly brackets or inside the two directives for Fortran. So here it says, if I am not the initial device, where the initial device is the place you start running, which is always the CPU, then say hello world from the accelerator. Otherwise, say hello world from the initial device or the host, and then ends. So most basic thing you can do, query the device, and then have a single thread on the GPU, just say hello. Okay, so let's compile this. You can do that just by doing make 0, 1, and this is 0, 1 target construct. So you can see how it's compiling, and you can ignore this warning message for now. And then let's run it.
Warning starts 23.1 or 23.3. The latest HPC carry is actually warning. You can ignore it for now.
Okay, thanks. And then we just run it.
I have a quiz. So what do you expect it prints? Accelerator or host? What's the printout? What will be the printout?
Is there an accelerator on this node?
So Colleen already grabbed an interactive job node. You see the name is at X blah blah. That is the Cray node name. So she's on the compute node. So if you want to know how many GPUs are there, what's the command you should run? Is NVIDIA SMI. Colleen, run NVIDIA SMI. Yes, it tells you there are 4 GPUs on the node. Currently all visible. So technically the GPU is there running. So how now if you run the target region, what would be the expected printout? Should be accelerator, right? Colleen, go ahead. Yeah, so it tells you there are 4 GPUs all visible to the NPM process, to this process. And it's on the run actually happens, the printout actually happens on the accelerator. The reason,
But only one of the 4.
yes, there's a default device. There's a concept of default device for OpenMP. If you specify target region device, put the number 1, you will hit the GPU 1, not GPU 0. But by default, it's GPU 0.
Okay.
There are 4 GPUs.
Yeah, this is
nice clause to control it. But usually we don't control it this way. Instead, we control it through the outside. We expose at most codes works best 1 MPI per GPU.
You bind the GPU to
yes.
Yeah,
so Colleen, could you do put the environment variable to the visible devices and run NVIDIA SMI?
device. Right?
I don't remember exactly. Name.
Yeah. Um, Maybe that doesn't work with NVIDIA FMI.
Well, it works. Anyway.
Well, what it
try
would work with is if I reran a one target construct, like before. So before target construct says there are 4 devices. If I put CUDA visible devices equals 0 here, now it only OpenMP only sees 1 device. So yeah, that's.
So you explicitly control the device exposed to that particular MPI process. Yeah. Colleen, could you play with offload target disabled OMP offload? No, what's the name? Amended.
Yeah, I got it. I missed the word.
Yeah. So in this scenario, yeah, it disable the acceleration, and since the OpenMP target region will be compiled twice, one for the host, one for the device, unconditionally. So when the GPU is available, it tries to run on a GPU, but now you're telling it, don't go GPU, just run a host. That's why you get to bring out on the host. It looks dumb, it's helpful for doing debugging. And also, if you are C++ code, don't try to see out, it won't work. Printf still works. So you have the final rescue, just use the printf. Oh, sorry for the interruption. Could you continue?
Yep, no, yeah, thanks. Yeah, thanks, Jay. Yeah, so that was the most basic possible thing. And like I think people mentioned, running on the device, we have a print statement on the device, but we're only getting 1 print, which means we're only running a single thread. And of course, we're not taking advantage of all of the stuff that's all of the compute resources on the GPU with a single thread. So the next example is just going through expressing parallelism. So again, Fortran is on the left, CLS is on the right. You can see how similar they are. This is where the team script parallel 4 comes in. I just added in SIMD because not all the compilers do anything with SIMD, but some, like the Cray compiler in particular, needs this to spawn all the threads. Other compilers will just ignore it. So I just put it here to be safe. But again, so this int main host thread on the CPU is running along until it hits pragma target teams script parallel 4. And then we have a loop just from I to 10,000. Inside the loop, we're not doing anything except printing what is happening to each iteration of the loop. So just like on the CPU, the iterations of this loop are distributed to all the threads that are running the GPU. So here we're just printing out who they are. So it says print for thread, OMP get num thread out of get num threads. So thread out of which thread, in which team, out of how many teams, it gets which index. So if you remember in the intro, we have a league of teams, so a bunch of different teams, and then threads inside of the teams. So sort of hierarchical. So this just prints thread ID in the team, team ID in which team, and who gets that index. And exactly the same with Fortran over here, except do instead of 4, and writing again, thread, get no thread out of how many threads, in which team, of how many teams. So let's.
Hold a second.
Oh.
In the Fortran code, I just want to remind you, although that OpenMP in Fortran, you can also like define external functions yourself, define all those functions, because there are users doesn't like to use the OMP lib module. Instead, they explicitly define Fortran functions that won't work with offload. You must use the Fortran module.
How do you
Yeah.
choose 10,000 numbers? On the C++, oh wait, which file are you looking at?
Sorry,
Sorry.
I'm misinterested. I didn't quite hear the question.
Oh, I was probably just looking, are you looking at the target teams parallel CPP, C++?
Yeah, this is the CPP one. Left side is the Fortran one.
Right.
Right side is the CPP.
Oh, okay. Oh, so I'm asking, how do you choose the 10,000 in the for loop? How do you choose the 10,000 number?
I just wanted to pick a big enough number that the output would look interesting. Let's run this and then I can go back and change the
So
number to something else.
you want it to be bigger than the maximum number of threads, or?
But, well, it's not, yeah, I just wanted to,
In
Yeah,
this
it's kind of
case, it's arbitrary, but it really depends on your physics.
Yeah.
So
This is
yes,
just-
you're right. If you have a lot of threads, your total iteration space should be larger. I would say 10 times of the actually total threads CUDA cores on the NVIDIA GPU. This is flat, so you have the teams and parallel all together. That's why the iteration space is larger. In other code, you can do hierarchical one. You have teams, you have 100 teams, 200 teams. Then each team's inside, you have parallel 4. You probably want like 200 iterations.
Now, you also have SIMD, so do you have actually 3 levels there? Where
Uh,
SIMD only works on the CPU?
Here, I would say SIMD is more of a hint to the compiler saying, yes, it's a parallel thing. Go figure out. Don't try to kind of prescriptively say you must do this exactly. SIMD should be warpable exactly. You better just leave the compiler.
But do you need the SIMD there, or can you leave it out? Does it do
You
anything?
can leave it out.
yeah, the
But some
only,
other places, some other compilers may do better job seeing the SIMD. That's
Cool.
yeah,
okay.
the only one I know of is the Cray compiler.
See, and that has 3 levels that you can expose.
Yes, you can.
You could do that also with the SIMD on OpenMP, or
You can, OpenMP, you can leave it there, but the compiler may decide to ignore it.
okay.
What are the levels of parallelism again? They're teams? Is it just teams or?
Teams and parallel.
Teams and the parallel and SIMD, but SIMD is very dependent on the compiler and depends on the GPU.
Gotcha.
So for example, Intel GPU with Intel compiler, they may use the eSIMD, the vector unit, to
Right.
explicitly take advantage of that. But some other GPUs like NVIDIA, they don't have SIMD hardware at all. Then their compiler.
No, but the NVIDIA has 3 levels. So
But their warp is not SIMD.
it's, no,
Yeah, it's more of, I would say as a programmer, as a co-developer, taking care of 2 levels probably is enough. If you will be,
3.
well, I mean, we ported it a few years ago to OpenACC for ProMotor, so. But before that, we had a work.
I think about portability, if you. SIMD, I would say, yeah, hopefully your code have a flexible, like a vector length, you can take advantage of.
It's a sparse matrix that's irregular.
Yeah, unfortunately, that's a bit
I know.
of gymnastic you have to play. Yeah.
We'll play. Thank you.
Yeah,
Yeah,
Colleen was showing something, yeah. Go ahead.
Yeah, I'll run that. Yeah, we're just in the slides in the morning in the backup section. I won't go through it because I think you already went through it, but there's the mapping really between like CUDA and OpenMP. So you can see the threads map to threads, or a thread to a thread. A CUDA thread, OpenMP team is basically a thread block, CUDA terminology. And actually we can see that.
Do you also,
Yeah.
hold on a second, do you also have the mapping to OpenACC? I think
I-
team would be a gang.
Yes.
And OpenMP thread would be that
Oh, you're gonna
worker,
put it in. Oh, no.
and the SIMD might be a vector.
I know.
Okay.
I mean, it doesn't.
Yeah.
Thanks.
I didn't quite catch all that. But maybe let me run this and then we can run a profiler around it and then can see how it maps to the underlying CUDA. So let me make, so the second one, which is going down to expressing parallelism. So it's something like that. Okay, and then let's run this. Okay, so I sort of chose 10,000 just because it gives us a lot of output to look at. So what we see first in terms of the like hierarchical threads is that we have 79 teams and we have 128 threads per team. And for every index, we see which that's all the indexes counting from 0 up to 10,000 minus 1. And we can see which thread out of 128 teams and which team out of how many teams is using the index. So this is really just to make clear, it's nice for sanity checking to see that yes, indeed, the threads are getting, the indexes of our outer loop are being split up into teams, threads in each team. The number of threads per team and the number of teams depends, it's up to the runtime of the compiler. So it would depend, maybe if I did 100,000 or something, we would get more teams. And I know, for instance, if from running this example with LLVM compiler instead of MVHBC, I also see a different number of threads per team and total number of teams. So this is up to the compiler unless you explicitly specify how many teams you want. So num teams and thread limit. So for instance, I'm just going to say num teams 2, thread limit 2, and then I can change this to 10 to make the output easier. And then just recompile again. Teams parallel. And then if I rerun this, so yeah, here only 10, so now we only have 2 teams, 2 threads per team, and of course they're all the different 10 indices are assigned to the different threads per team. One thing to see how this maps onto GPUs, we can also use the NVIDIA profiling tools. I use this later, but we can just do this now. So Insight Systems, which I think there are talks about later, you can use this to see what's happening at the lower level. And this is important. I think to mention this, the 2, because at the end of the day, OpenMP is just sitting on top of NVIDIA and CUDA. So any CUDA tool will still work to profile OpenMP offload on top of CUDA, because at the end of the day, you're just doing CUDA runtime calls. I'm just gonna copy paste this because I always forget. So this is asking, so this was collecting the data, putting it in output O2, and it's just running the executable. And then here, I'm using the output of the run to tell us the CUDA GPU trace. And I wanted, I wanted to use this one in particular because, so this tells you a trace. So the calls that are happening on the GPU. And I'm gonna remove all this information so that it's a little easier to see on the screen. So we're only doing one call because that code just had an offload call, but it tells us in a timeline fashion. So for the next example, we'll see more. Like kind of, so I would have more things happen on a timeline at what time. Here, what I wanted to point out was in CUDA terminology, again, you have a grid and you have blocks. So like when you right in CUDA, you have a triple chevron with a number of blocks you want to launch and then the size of the blocks. And that you can see here with the grid dimension for the number of blocks, and then the block dimension for blocks X, Y, Z. And this, you can see how it maps directly onto the OpenMP offload, num teams, and thread limit. So here we were launching with num threads 2, and we see a grid size of 2. And we were launching with thread limit 2, and we see a block size of 2. So at the end of the day, just this maps into CUDA. And profiling tools will show you your offload regions. I'm sure Ye will talk this more, but in the debugging, but yeah, tells you offload region, routine name, and the approximate line number. I hope did that clarify things.
If you came from CUDA programming, you know that the block size randomly here gonna affect performance if you need to fine tune it, right? So because each thread need a resource, need a register, you may find that having a too large thread count block size, limit large, it's gonna overspill to the global memory. So you want to restrict. In that scenario, you could leverage this option thread limit to cap the number of threads per block. And grid is the same situation. If your kernel is lightweight and you do have concurrent kernel execution, you have another kernel on the fly, could also use, you don't want this lightweight kernel to block the whole GPU, use all the 80, 100 SMs. You could also limit a team number just to say, stick to the 2 and loop over it. So to run those lightweight kernels to reduce its cost. So these tunable parameters are available for you. Number of teams, thread limit. That's the purpose.
I just have a question. So when you're running I less than 10,000, why did the run stop at I equals to 2309 or something like that? 23 something.
Yeah, so it was looping. It was just the code just had a loop from I equals 0 to whatever it was set to. So initially 10,000, but I changed it just to 10. So the loop itself.
I was asking before you make the change. You look at your run the first time, it stopped at 239 something like that.
Yeah, so just because the thread, this is running in parallel, so it comes out in any order. It doesn't actually stop there. It's just the print buffering or whatever leads to 2399 coming out last. As you can see, like 9,000 is before it, but it's just because we're running in parallel. So anything in that loop could happen at any time. You can probably find, yeah, this was printed closer to the beginning. So that makes sense. It's just like, even if you're running on a CPU with a bunch of threads, if you run the threads in parallel with Pragma OMP parallel 4, they could have happened in any order.
Yeah, thank you.
Yeah,
It's a little bit small, so it's a little bit hard to see the numbers.
Oh, okay, is that better?
Yeah, but I understand that. Okay, thank you.
I had another question. So I remember at one point on CPU, at least with the SIMD directive, we were making some guarantees to the compiler about potential data dependencies between iteration.
No, data alignment.
Or maybe it was data
Alignment
or something.
yeah.
Are there any of those kinds of concerns that you have to worry about with just with adding SIMD? Like, I assume that you're not allowed to have loop carry dependencies or those kind of things.
Loop carry dependency, no, with SIMD or even on GPU programming, forget about that. Otherwise, you don't have performance clear. But be careful. You can have between teams,
can have some.
you can have some, but just be careful. In CPU, when you use SIMD, you specify aligned, right? There's a clause called aligned. Yeah. it's a hint, it tells the compiler, I guarantee align, so there's no peeling loop, no.
Yeah, if you
Yeah.
didn't give the align,
If
it
you-
said there was a P loop,
Yeah.
then the align part, and then at the end there was a, if it's not, it didn't end on. Yeah, I remember that from.
But if you don't provide that, it's still valid. It's like you should not worry about. However, so it's the same situation in GPU. I would say, I haven't seen overhead on those peeling loop or the.
What were they on KNL? I remember you had all of those loops implemented manually. Where you had a few, you know, the.
Yeah, no,
The
that was
key
more
part is.
complicated than that, but yeah, let's not go into those details right now.
So the key part is you still need to do alignment on the, when you allocate the memory segments. That's still a performance benefit. You should do it if you are looking for the performance. Whether providing this aligned hint or not, I would say that impact is minimal.
Yeah.
Yeah.
Okay, thanks. I think no more, it sounds like all the questions for example 2 are resolved. Great. So then the last example is sort of more like the hello world of HPC, which is a vector addition. And it's this because so yeah, we talked about how to run the GPU and then how to express parallelism. So you have a bunch of threads running all across the GPU, but of course we need our data on the GPU to access it. So this is a data transfer example. So again, on the right, C++, on the left, Fortran, you can see they're doing the same thing. So in both cases, we allocate 2 arrays A and B of size num elements, malloc allocate. We initialize A and B on the host, setting A to 0, B just to the index J. Then we want to actually do some kind of compute on the device. I'm just gonna line these up. So like we saw before, target team distribute parallel for SIMD or parallel do SIMD. But we want to put our arrays A and B on the device so that we can do a DAXB or a vector add. So take A, add it, or take B, multiply it by scalar, add it back to A. So we need to do this, we need to send array A to the device, to the GPU. And then we also want it back at the end because we want to do error checking on it. And that's the array we want to use. So plus equals or just A equals A plus scalar B. B, we only need to send it to the device because we're just reading from it on the GPU. We're not writing to it. And generally, the data transfer across PCIe to the device is an order of magnitude slower than reading from memory. So generally, avoiding data transfer if you don't need it is a good idea. But once we've added A to B to scalar, we're done. Transfer back to the device from, check the error, and then free memory. So that's just the setup. So,
is there a reason why on the Fortran you have an assignment and in the C++ you have an addition?
The plus equals.
Yeah, is there any reason why?
Fortran doesn't have, at least the Fortran I'm familiar with doesn't have plus equals. But that did remind me of one thing I wanted to point out was one difference you would all see is in C++ when we're mapping, we are specifying the number of elements. So not just B, but B, and then the array, there's an implicit 0 with the length of number of elements, both for A and B. And then Fortran, we don't do that. And this is the one reason here is because in Fortran, these are allocatable arrays, and in Fortran, allocatable arrays save how big they are. So there's no need to tell the runtime how large of an array to move because it already knows in Fortran. So Fortran, this is one nice thing about Fortran and OpenMP. So you don't have to also add the size. In C++, A is just a pointer. It doesn't know, it doesn't tie the size of A to A. So you have to say how big also. So that's one Fortran C++.
What happens if can you use OpenMP map with sort of non-fundamental types, like if it's a std vector, can you use map? Because then the vector would have the size information. And also in that case, does it call the copy constructor, the move constructor? Does it just copy the memory byte wise?
I'm trying to go down that rabbit hole, so the boundary between CPU and GPU is pretty tough, yeah. So basically, reliably just transfer plain old time information.
Because that's gonna be, I have a
You
different
can.
I have a different code that's very object oriented.
You can have std vector. It's not a problem. Std vector, when you use it, just around your, because think about your OpenMP kernel offload region won't be huge. It's usually quite by itself. So around there, you extract, you do vector.data, extract the host pointer and do map. Or you have allocators pre-map this data segment. That's also very doable. So when you use it in the code, just expose the raw pointers.
So the other way to do this is with custom allocators and allocator schemes.
That handles the mapping, but that doesn't change the fact you still around the offload kernel, you use the pointer.
Right.
Yeah. Anyway, you don't expect to resize on the GPU. You only expect to resize on the CPU. Right. Yeah. So just one quiz. Well, we are using the scalar on the GPU. Why we don't need to do data transfer?
Because you haven't declared default none.
No, because scalar is a scalar.
Yes.
Right,
So,
but also you haven't, if you said, I assume that OpenMP still has default none, in which case you would have to declare everything.
it's got default map now. It's in the threading case, it's default now.
Okay.
Then you won't get default shared this other variables. I think in offload case, it's got default map now.
Gotcha.
Yeah. Here is, as you said, its scalars are first private by default. So first private is a very helpful, performance-friendly optimization because the runtime won't issue a data transfer for a scalar that is 4 bytes, 8 bytes. Instead, it will be part of the kernel launch parameter. It's kind of hidden from the transfer. So it's super cheap. It's like you don't feel it. So don't try to map scalar. If you explicitly specify map scalar, map to scalar, it will be actual memory transfer call, which is super expensive. So don't do it.
Now, you say scalars are first private, but if you would have, say, a sum with a reduce, then the end result would also be transferred back to the CPU automatically, right?
In the case of reduce, actually, you have to transfer the initial value in, do the reduction, transfer the value out.
Oh, that you have to do explicitly?
No. Reduction. If you have reduction from OpenMP 5, 4.5, you need to do map to from, but from 5, all the reduction parameter is to from by default.
Okay, and does OpenMP do a reduction on an array?
That
Yes.
experience really depends on the vendor.
We use that.
Let's say the vendor is Intel.
Intel seems supported, but
Okay.
this vector may have a length limit.
Don't do it on a big factor because
Yeah.
then you're in trouble anyway.
Yeah. Because for vector reduction, array reduction, there's no single scheme suited for all scenarios.
Yeah,
The
yeah,
developer have better ideas how to do it.
I've been through this a few times.
Okay. Colleen?
Yeah, so let's compile on this. So just, I'm copy and pasting, so just make O3 map. So compiles, good. Enter, and let's run it. O3 map. Success, because it had error checking in it, so it's just selecting. So the success just means it ran it, it got the correct answer, there were no zeros, so that's good. But kind of related, since we're interested in data transfer and kind of related to what someone mentioned about the map clause, we can use the profiler to again look at the data transfer. So this is the correct options to give to Insight Systems to ask it to get a profile, and then we can look at the trace. Similar to last time, this is more interesting because more is going on. And again, I'm just going to remove some of this. Just so everything fits on one screen. That's almost there. Hopefully we don't need to group it. So again, timeline with timestamp start. So first we see the first thing was a CUDA mem copy, host to device. Oh, and I removed the size. I can get and I'm just gonna rerun this. I can keep the size, but nice to be able to look at the sizes. Okay, yeah. So we have CUDA mem copy host to device, two of them, both 0.008 megabytes, so 8,000 bytes. And then if we looked back at the code in both cases, this is 1024 elements, double precision in both cases. So that matches 0.008 megabytes. So we use 2 copies from host to device, which is exactly what we asked for here. Map 2 from A, so 2A to B. And then we see the call to the offload kernel. And then we see one more copy device to host, single one of 0.008 megabytes, which again was this from so mapping A back from the device to the host with the new result, which we then use to do error checking. So this is really nice to check what you think is happening is happening. We could do what someone mentioned in map to stellar. Save that, and then if they compile, and then just think I need to new older one, just rerunning with profiling enabled, and then rerunning. Now we see this. Okay. Just move the block size. Now we see this extra, it's less than a megabyte, so we don't even see it, but we see this extra CUDA mem copy host to device, which is just transferring that scalar, which of course we don't need to do. Like Ye was saying, this is passed as a kernel argument, which is a nice optimization because then we don't have this extra explicit mem copy host to device. So hopefully that makes sense. Yay, any comments before moving to the next one.
Yeah, let's see the next one.
So now this is a really simple example. So next, let's do slightly more complicated example. So we're gonna get two more examples that are complicated. So here, this is still the basic DAXB again, where you're taking two arrays, add them together. But here, we want to call it twice. We want to add not just a equals a plus p times scalar on A and B, but also to C. So we want to call it twice, and we want to be good programmers. So we know we need to do this twice. So we put it in a function called DAXB. But here we want to do A equals a plus b times scalar, and then using the result of that, add it to different arrays. So C, here we have 3 arrays, but the basic structure is the same. Allocate 3 arrays, ABC, initialize them on the host, and then this is exactly the same as last time. Get the result of A equals a plus p times scalar, put it in A. Then we want to say, okay, C equals C plus A times scalar, put it in C, and then do error checking and free the arrays. So just again, the same thing, C plus side on the right, portrait on the left. So this is just to make it look a little more interesting, have a little more going on. And the offload regions are exactly the same, mapping to from A to B. So let's compile this. Complete. Okay. So we compiled it and then run it just to do sanity checking that we get the right answer. Good. We got the correct answer. So let's just look at the filing output again. So running the profile. And let's look at the trace. And I can just up a little bit. Removing a lot of columns to be able to fit everything on one screen. Okay. So what do we see here? So again, you sort of see what we expect. We have the A and the B copied from host to device, again, 0.008 megabytes. Then we have the first call to the DAXB, so function and then line number. And then we got the results in that array A, mem copy from device to host. Then we hit the second invocation of DAXB. So again, we copy A and C, host to device, call the offload kernel, exactly similar as before, just different arrays. And then finally copy C back from device to host. Just a reminder, so that was this. The 2 DAXB calls. 2 DAXB calls where it calls OpenMP target team 0 parallel 4 SIMD twice. So hopefully that makes sense. But then, of course, the question is, this is a lot of data transfer. Do we actually need to do this data transfer? Because what we can note from looking at the code is that, yeah, we got the result we want in A, but we then immediately reuse it in the second DAXB, and we're not doing anything on the host in between the two. So the copy 2 back to the host is not necessary because we just reuse it from the device. And the problem here is that if you use data mapping this way in OpenMP, the data transfer is tied to the target region. And we definitely don't want to do it here. We want to do data transfer in a way that it's not directly tied to the kernel launch. And that is our final example, just to show how to do that in OpenMP, because data transfer is expensive, so very important to know how it works. So here, the code is actually, we leave the map as it's in, looks exactly the same. Only difference is, scroll down, is here. So the unstructured way of mapping data in OpenMP. There are a couple of other ways, but this is just one that I think makes the most sense here. This pragma-OMP target enter data map 2. So we take ABC, we have them initialized, map them to the device, then all the routines, and OpenMP has tracking of data on the device. So even though we have the maps here, it already knows they've already been mapped to the device. So I'm not going to remap them. And then at the very end, just update from the device for C. So we are doing just the bare minimum amount of data transfer we need to do in this case. And then same thing with Fortran over here, when we target enter data map to ABC C. Oh, so it's, we lost. I know they can get it soon. So let's compile here and just compile this last one and then look at the trace again to see what's ended. Compile. So success. And then I'm just copying this. It gets to be a lot. So the profiling output. And then let's look at the trace. There's this. Okay, so this looks much better. We have the 3 copies of ABC from host to device, 2 kernel calls, no data transfer needed in between them, and then copy back the result from device to host. And compare that to this, where we were doing 2 calls and then a bunch of 3 calls in between, and then 1 call at the end. So just, maybe takeaways, data transfer is expensive. Try to avoid it, but also these tools are very useful for checking if what's happening is what you think is happening. And that's all I have for this. So yay, any additions?
There are questions, go ahead.
How does OpenMP keep track of scope? So like if you do the unstructured map and then the host variable goes out of scope and like it's something that like has a destructor or something and that gets called. And if things go out of scope, does that memory get leaked on the GPU?
Yes, you get leaking.
Okay.
So,
And I mostly actually I was thinking on Fortran, because if you have an allocatable array that's subroutine local, you can call deallocate, but you don't have to. Fortran guarantees that it will get deallocated at the end of the subroutine. But will it leak if you
in the
don't?
Fortran case, you still get leaking.
Okay.
Oh,
So if you don't do exit data,
Automatically, no.
okay. Is that
I fight with the spec about this for a long time, and I cannot convince these guys to implement.
That's not the way that Fortran works. I agree.
Exactly. So, but my recommendation is you develop some layer, because Fortran you have the final clause in the object-oriented Fortran. So you try to implement the data structure with that cleanup step embedded into the final function to avoid leaks.
And then
That will be automatic.
the other question I have is, are these, well, in Fortran, I guess they would be called save. In C++, it would be static. Or are the on-device variables effectively static in the sense that if you don't exit data within a subroutine call, the next time you enter the subroutine, that is still there? Like, you see what I mean? Like, you can, in C++, you can declare a variable static, and then every time you enter the function, it will have the value it had the last time.
I think
Fortran
it will
you
be,
call save.
yeah, I think it will be static, also static on the GPU. It will be resident. Because they, Colleen, go ahead.
Right. Oh, no, I was gonna say, yeah, I think we would have to test that. I think in theory that should work, but also we would have to
It may be a side effect.
try to
of the
see, yeah. I was
I
trying
know
to think if
that
there's. Go on.
Local variable, if you declare static, declare it as static, and you have declared target around it, that's guaranteed to be resident on the GPU. The static variable inside a function, I'm less sure about it.
You are, I mean, does the runtime go off of the host's memory address?
Yes.
Because you are guaranteed that a static function variable
Yeah.
will have the same address every time you call. And if
Yeah.
that's all that matters for the
Yes.
mapping on.
The mapping is purely based on the starting address of a point. So variable is also as a point of size of a specific size. So it's just memory address purely based on it.
So that's why.
Go ahead.
I have a different question. In principle, you only need the array C on the device after the first DAXP. With OpenACC, I would do an async on the data transfer of the array C, and then a wait in between the two DAXPs. Is there something similar in OpenMP?
You don't have explicit control of streams in OpenMP. So async, ACC, you async a number, right? You specify.
Yeah, I would say transfer this data, and then a little bit later, I would say wait until the data is transferred and then start with.
So in OpenMP, what you can do is using task. So you do
Okay,
async.
I've never used tasking, but I've heard of it.
Enter data can also, you can say no wait. So the transfer will be asynchronous. And later you put a dependency, say depend on the C segment. Then the runtime will.
Oh,
figure
yeah,
out.
I've used no wait with OpenMP, that's right, on just on the CPUs.
Yeah, that's slightly different,
Yeah.
but think about it, it's just turn no wait task, target no wait is basically a task.
The task, and I just have to make sure that it's there by the time I do the DAXP is set. Do you have an example of that?
Writing one.
Yeah, I mean, I think this might work, although I'm not sure because you call an offload region in between. So I don't know if that would itself count as a wait. I can try with. Yeah, I'm not as familiar with this. I did at least. I did run correctly. Yeah, it's also, it would depend on if NVIDIA compiler implements that.
NVIDIA doesn't support task.
Oh, then okay, this probably won't show any difference in that case.
So is with the
Yeah, it
array,
looks the same.
is there any way to overlap? If tasks are tasks supported or not?
I think it doesn't support task at all.
So there's no way to overlap the communication at
Oh, LVM, yes.
Well, also for communication, that would be a problem.
Yeah, so.
Yeah, that's why our code hides the computation behind the communication. our runtime is completely dominated at large.
Well, for
scale.
big runs, not
big
for
runs.
all runs.
For big runs, we're dominated by.
Yeah.
Not
I'm not even fully sure. I know maybe it supports task, it doesn't support task group of. Anyway, the tasking in the NVIDIA compiler, the PGI compiler is very limited, I would say. It also
But
doesn't
it-
support like user-defined reduction. They don't give me such things.
No, user-defined reduction,
Uh-huh.
but that's in the standard for a long time.
Yeah, they don't support user-defined reduction.
Yeah.
Because I have arrays of X, Y, Z, fixed size array, and it's no difficult to define user-defined, and there's no point involving because it's purely on the stack operations, right? Then they don't support. They do support like stud complex by pattern matching, I assume. So you can't use user-defined reduction. Yes, NVIDIA compiler, that the PGI one, this has a lot of limitations.
Maybe there is a reason we
Who's my
use.
fourth secretary?
Yeah, we did. No, I remember this discussion years ago. There's politics going on.
Yeah,
That's what's going
yeah,
on. This.
but the Intel compiler will
Intel,
support
yes.
that and then the.
Intel compiler is LVM based. LVM supports all the spectrum of features.
Okay, but the Intel compiler will never support the base system.
Yeah, I know, that's why we changed the code.
Yeah.
It means we still have a job.
It does. Maybe four, three, four.
So technically, you can inside the DEX be around the target region, you put all the dependencies, ABC, all the three, as a generic function. Then,
Can you also, instead of, or at the moment in the function, you still have the mapping. Could you, instead of a map, if you, what happens if you leave that map out? Because the way you've written it now, you don't need the mapping there, right?
Yeah, correct. But yeah, it's the same. I mean, it will still work.
It will still work. Is there a way to indicate that it is already present? Because I think that's what I do with OpenACC.
yes, there's a present check,
Okay.
but you will need a map.
Oh, the map does essentially do a present check?
No. Yes, okay. Map itself always do present check, but it's not a safety present check you want. It's doing reference counting, need to check if you mapped it already or not, and decide whether you transfer or not. It's not
Okay,
your
so-
purpose. But in the map too, you put comma present, it will do a present check. If the reference counting, your reference count was not already positive, it will error out, telling you.
And if you don't have that present, it checks whether it's present and only copies if it's not there. Okay.
It's a bit hidden. If it's right, everything's right, seems fine, but if you mess it up, it will still run, you get performance penalty. So present check is an important feature. It was added, unfortunately, later, it's like 5.1 or 5.2. Yeah. And they also, in the past, you need to do 2 comma present. They actually have a way now to, you don't specify 2, you just put present. The more intuitive,
Okay.
because you only want, you guarantee that it's already present. Your intention is to do a check using the resident version data copy. Yeah.
Is there an equivalent in OpenMP to ACC routine? Where you declare an entire function or subroutine as being entirely on the device?
Yes.
And I know that I have used that before to avoid extra kernel functions. So that if I have a function that I want to call from its like I have some complicated subroutine and all of it's on the device. And I want to call, but I don't want to launch a new kernel. I'm in a kernel and I want to call.
So think about, it's similar, like you have a sine function. Now you want to supply your own version of sine function.
Right.
So yes, you use declare declare target around the function. Yeah, you do this.
I think we also did that for certain arrays, declare create.
Declare create was more like, I guess, declare create is more like target the enter data.
Yeah, declare target create is for data, not for function.
Yeah.
Yeah.
No, it's the ACC routine.
I don't, did we use that?
I used it in the VC, but I don't know if we used it.
I don't think we used it. I don't know, we started with an older standard.
Oh, so the declare target does need an end, or is that just a good habit?
I recommend you put in that. It was not a big issue in the C side, C++ side. It was a big issue in the Fortran side. The compiler developer figure out without an end, they find it's very hard to define where to end the compilation unit,
Yeah.
translation unit for the compiler. And are we supposed to have a break?
I think not.
Well, if you look at the schedule, it's very weird. Time it's all messed up.
We can take a break right now. Sure.
I think we have to end at 3:45 because of the tour.
Only for those people who want to go on the tour.
Oh, really?
It's a big machine and it's over there, right?
What's over there?
It's a big machine and it's
Oh,
over
the
there.
machine is upstairs, isn't it?
No,
Yeah.
it's in.
Yeah.
Yeah,
It is
the
up,
other-
it is up in a layer because we're on it.
It's up a layer, but not above us.
We will have to see.
Yeah, maybe if you want to do the affinity one.
I think,
Because of where you RC makers.
that was
Is it like trying to put them on the main bin or something?
I think I tried to probably cut short the affinity portion. I don't. Yeah.
Your student just decided
actually-
to walk out of class.
I did a debugging one.
Yeah, probably I will run the debugging.
Yeah, I think that's probably the most useful. And then if we have time after the affinity one quickly, I think
We could do that.
my voice is going away.
You really lost 2 students. Or 3, actually.
Between now. Okay.
This is a hands-on. We haven't done anything hands-on yet, right? We can do it at home.
They give you a allocation.
We can do it anytime.
End of the month, probably.
But anyway, it's very helpful. It's eye-opening. It shows me how much I don't know.
More you know, the more you
Yeah.
understand.
I
the
just-
little you know.
The more I know, I just know that the more I don't know.
Yeah.
Yeah.
Choosing a flat programming model is very subjective, I would say. It just, you see all of them seems all working. And if you use them wrongly, it's just terrible anyway.
So what's the definition of a good model?
Programming model is something beyond your base language. So if you think Fortran, Fortune C++ is a base language. Then programming model is things built around it.
What's the definition of good? What makes
Good is about your code maintainability, portability, it's productivity, portability, that aspect, performance also. So it's like, if you use OpenMP, even just on CPU, you can write a terrible OpenMP code which doesn't scale in threads. If you just directly throw some random parallel flow, you won't get things you actually want or you can potentially have.
So it's good scaling, has to be fast, and things like that, right?
Yeah, you have to be flexible.
Easily
You don't want the
upgradable.
algorithm runs on 2 threads, 4 threads doesn't work on 10 threads. That kind of weird situation.
But no two is perfect for every situation, right?
Well, as long as, yeah, that's why it kind of, we don't ask you, tell users you should use this programming model or that programming model. You need to make a decision based on your need.
You can use J.
Oh, okay.
Achieving a simple goal requires me to write tons of lines to set up the runtime just to schedule things. That's an overkill, I would say. It's not helping productivity. And also, yeah, the more you do it yourself, it's further error prone. So try to avoid doing that. On the other hand, you have something in the between, like you have OpenMP between you and the kernel, the user code to the kernel. There's OpenMP in the between, doing all the heavy lifting works. Yes, debugging wise, it will be a bit more difficult. Similar situation for the C++ based programming models like Cocos Raja, those things. Yeah.
So is OpenMP better than DPC++?
It's different things. As you said, it depends on your use case.
But which one will be faster?
If you see the benchmark, they show you at that speed, they are equally fast because it's just so simple that at the end of the day, the kernel generated is the second. Then
You talk to who again? Sorry.
XP,
Oh,
like AXPY. If you say, well, can we implement a matrix multiplication, use these two programming model? Neither of them will give you the best because usually vendor program at further lower level, yeah, to get the maximum performance. So it's likely depends on what is your programming language. So if you use like SQL or VPC++, with Fortran, you have to manage the interface between Fortran portion and the VPC++ portion. Then using OpenMP would be a lot easier. If you are already C++ taught, maybe you want the SQL portion just naturally C++. But my experience is OpenMP still does a pretty decent job. Yeah, because even you use SQL, the SQL has a runtime built on the vendor lower level software, the runtime systems. So that means, yes, you have SQL portability across all the GPUs, but your performance is subject to the runtime, how good the runtime is being implemented. Then that's also an open question. So you have to figure it out. Like in my experience, I really want multi-threaded offload, multi-threaded kernel launch. Everything needs to be multi-threaded. But a lot of application just need one thread talk to the GPU, like always. It's a fork join. Like, okay, you have OpenMP CPU, you have threaded area, but when you call GPU, you never call from threaded area. You always call from the serial area to to the GPU. Before, like you call a threaded jam, now you call a GPU jam. So that kind of things. So in that scenario, pressure on the GPU runtime is a lot lower. And you may find all the vendors are doing pretty well already. So it's very demanding. Okay. I just planned something.
I have one question. So you said you work on the finance ratio. You also work on the math.
No. Yeah, that is the Vienna people plus NVIDIA are taking care of that, so it's fine. Well, we do have fast users, and it just means that don't work on the code. I'm not allowed to work on the code. No, I have no interest. That's different thing.
I'm also a user.
Yeah.
And the two, it was just normal scoring was found, right?
Okay. So I'd like to give a bit tips on debugging.
Oh, actually, yeah, I didn't, yeah, so.
And just an interactive job.
Enjoy being my note page from now on.
But this.
Oh, it's not.
We have a reservation for the next 3 days or so.
Just messaging me, so I was taking notes, so like I won't.
The reservation ends at 5 PM or something like this.
That I don't remember, probably a bit later. The allocation will last longer. You can most of the time you just grab one node from the debug queue, regular debug queue.
It was until
And you
5:30,
can
and I was like, okay.
play with things. So okay. One point I will do. Probably experience. So yeah, actually the GPU code, GPU programming, it's even worse than debugging side because you have two memory spaces, the host one and the device one. There are ways like you use unified memory to avoid those, but usually you have a performance hit. And when the error happens on the GPU, it's usually harder to debug. So how to debug code? One way is with OpenMP, one way is you try to think about when you develop a code, you have to do a mental exercise to see if the code is not offloading, does it still run? So you need to design it that way. So that's why a lot of times I say, don't use use OpenMP like a CUDA. So in CUDA that you allocate a memory, the host pointer called A, you need a device pointer called A_D. You call CUDA malloc to allocate. Then you will constantly maintain two objects. And if you compile it for CPU, if that's the A_D. So that's a scenario that's very ugly and very hard to maintain. So, but with OpenMP, you have A and you always map A. Then the map A itself is when you don't compile OpenMP offload, it disappears. So you try to see if your code just works by itself without activating for the offload. That's the best scenario. Once you maintain your write your code that way, now you can just debug first on the CPU. Because if you have like out of bound access, like your iteration space go beyond the range of the vectors. You can catch it on the CPU. You have all the CPU infrastructure to debug. Debugger, sanitizer, you figure out all the problem. So kind of you have a first level defense by just running it on the CPU. Very useful.
Wouldn't PAL and something like that be able to do something?
Yes. I'm saying that you do need to first design your code in a way that if OpenMP is not active, offload is not active, it still works. It's like OpenMP threading. If threading is not working, the code should still run, give you the right number. But with the GPUs, you need a bit of effort to design it that way. If you try to use OpenMP functions to allocate device memory and you end up with A and A underscore D, the code won't be so friendly to you to work on the host and device together. Just that kind of tips need to give. So if your code is designed properly, I haven't found the situation I must, this strategy doesn't work. So I always find it, if you design your code properly, you can have your code end up with at least running on the CPU. It doesn't mean performance on the CPU, at least it's running on the CPU. As long as it's running on the CPU, you can do a lot of extra effort to improve the quality of your code tool with all the tools. So compile without offload, get your code to run. This is first debugging you could do. Second is debug on the host, but with OpenMP turned off. You could also try it to see if it runs. The worst scenario is you do print off F, or you try to transfer all the data back to host and do it check on the host. Okay, let's go to see this very simple example. I just write this buggy code. Yeah, very minimal. So we can exercise the strategy. So actually, this one is. So I'm doing one thing. I have A and B is a vector. I just want to bring the result from the GPU. So maybe for others' curiosity, can we just do the vector on the GPU? So I just I don't know what's wrong with my.
Okay.
I just have to do this. And just put a B here. Put that directly in the target region. So. You just try the basic compilation and see what happens. Oh, sorry. You just compile it. So if you use clan, you can check. It didn't say CUDA means it's not finding the CUDA tool yet. Load module. Probably a new one. So you will see an additional line is CUDA because it depends on the library from CUDA toolkit. So now we can compile it. And you get those warnings because the compiler doesn't know how to deal with those fancy structures, not plain old type. And when you run the calculation, it just freak out, doesn't know how to deal with things. So that's why. Like a particular size of the screen.
Yeah.
So what I do is I extract the points, data point, the raw pointer, pointing to the data and use it in code.
We just need to change something.
So it's something to do with flag. I'm going to use your brain and I'm going to use.
So in this example,
Just a stupid.
we compile and run it, we run into see this error message and illegal memory access was encountered at a stream synchronization. So the LVM OpenMP runtime, each OpenMP target region, it picks up stream, do data transfer, kernel compute to do the final transfer back and stuff. So that's why there's a synchronization at the end. And it reports an error saying invalid memory access. So how to look at it? So let's use the strategies that first try it out, see if it works on the host. That is, you compile it and select and type it as the x86. So you offload to the CPU. Oh, actually it runs and the numbers are expected one. So what can be potentially wrong? It says invalid memory access. So it tried to dereference a point, which happens on the GPU, and they could not find it. So this typically indicates we were missing some data transfer. If you're not fully sure, you can try to rely on the you could use a bit of tools that you can use like a CUDA-GDB, a debugger to help you at least tell you where it stopped. So you just run and do a run. Oh, this was fine because I was offloading to the CPU. So we need to change it back to offload to native. Yeah, it was code dumping. And you do the CUDA-GDB and run it. Oh, it tells me there's this kernel having a illegal address. You know that it comes from this specific kernel. Simple. You don't have further information because there's something missing. I only know the function name. It's the entry point for the function. How to fix that is you need to compile with -g. With the NVIDIA compiler, you need to put dash lowercase g and dash uppercase g to get both the host and device side. So let's see what happens now. You run it again. Okay, now it's better. You have the line number. You even have the core stack basically. So it's from the bug CPP line 11. It's doing something and it's printing out to you the issue was this printf. So something on this printf, there's an illegal memory access and it can only happen on the B, right? A is a scalar. It was fine. It's prefers private. You don't need to worry about. So you have B_PTR. So it's very simple. we're missing something that is actually the data is not available on the GPU. So debugger give you those basic information and you can avoid struggling. And just do a map too.
I gotta go on the tool.
Yeah. Yes. They said 3:45, right?
Yeah.
Yeah. So basically you add the debugger, add the data transfer and you get the number right. So, I mean, use the debugging tools that you can figure out a lot of informations. Try it out for your particular need. Okay. Go ahead and enjoy the view, enjoy the show.
Yeah. Thank you. It's very helpful.
Yeah.
Enjoy it.